Jnanam paramam dhyayam. Knowledge is supreme.
Let us start with an example to motivate everything that we want to do. Let us look at a matrix 2 by 2, simple matrix, right? Minus 5, 2, minus 7, 4. Let us compute what happens when you multiply, okay, multiply A with this vector 1 minus 1. Why I have chosen 1 minus 1? I will come a bit later. I will tell you why this special matrix, this special vector I have chosen, but let us just for the time being compute this product. So, A is 1, this vector is, so what is the product? Minus 5, 1, right, minus 7 with multiplied by this, so what will get? Plus minus 5 plus 7, that is 2, so similarly other one is minus 2. So, ordinary product we are doing matrix, and that is I can write 2 times, I can take out 2. So, this matrix, right, with respect to this vector 1 minus 1 has a special property. A applied to this vector is 2 times the same vector, right. So, what is it doing? So, this matrix A is just changing the vector 1 minus 1 to a scale, it is just stretching it kind of thing, right, 2 twice. It is not changing it to anything, it is just stretching it, that is all, right. It lies on that line minus 1 1, right, 1 minus 1. So, it was this vector, now it is stretching twice of that, nothing more than that. Okay. So, here is a question, given a matrix A, how to find all vectors that are scaled by it. For this matrix we have one, I have given you, how I got it I will tell you soon. So, that is one. How to find the scaling factor of a given matrix? Given a matrix, does it have some property that for some scalars there will be some vectors, say that A applied to that vector x is will be lambda times applied to that vector. So, what are those scalars, right? How to find those scalars and how to find corresponding vectors, right, which tells that it scales it. So, this is, and why is this important? Why this all exercise we are worried about it and why it is important. So, these 3 questions we would like to answer. Okay. So, let us look at one by one. I will keep this example in mind for the time being, we will work out with this example only, so that we understand everything, right. So, the question is, given this matrix A, I have selected one particular vector 1 minus 1 and which has the property that the matrix A scales it. It scales by a scalar 2, I know the scalar, I know the vector which is getting scaled, right. Right. Actually, if I take any other vector with this, say if I take 5 minus 5, that also will be scaled, right, but the scaling factor will be different then, that is all, right. But if I keep 2, then it will be same, 1 minus 1 will be scaled by some other factor, but if I take 5 minus 5, then it will be again 2 times 5 minus 5. So, it along that line every vector is getting scaled, that is all, whatever vector you choose it will be scaled by twice of that, right. So, the direction is sort of important. So, let us look at. So, I am rewriting it, A applied to that vector is 2 times that. So, let me take it on this side as a matrix equation. So, A, so when I take it on the other side what I get? A minus 2 times identity matrix applied to 1 minus 1 is the 0 vector, right. I just brought it on the one side. I want to make it look like a homogeneous equation now, kind of thing, right. So, what is saying is, so let us 1 minus 1 is a vector which lies in the null space of A minus 2i. So, let us put the null space of A minus 2i as a set, let us call it as V. So, V is all vectors which are killed by A minus 2i. So, I have got one element in that, right, 1 minus 1 is in this, right, is it okay? See, the a minus 2i applied to this was 0. So, 1 minus 1, that vector belongs to this set V, right. Now, so and we have already seen that a homogeneous system, this is a vector space, right. Any matrix applied to x is equal to 0, all such x give you a vector space. So, this is a vector space in which I have gotten one element, and this is a subset of R2, right. So, what could be the possible dimensions of this subspace? Already there is a non-zero vector, so it cannot be 0, it has to be at least 1. It could be equal to the whole R2, right. So, whether it is equal to that or not, we want to know that, right. So, what is the dimension of that? Means what I am looking at, what is the nullity of this linear transformation, right. In the earlier language, a minus 2i is a matrix. I am looking at the dimension of the null space of it. I already have one non-zero vector, so it has to be at least 1. Question is it more than 1 or not, right. So, let us look at one way of looking at this. We look at this matrix of a minus 2i, right. I am looking at all possible solutions, right, looking at all possible solutions. Now, if this matrix, if you have a matrix Ax is equal to 0, okay, and the matrix is invertible, then what are the solutions? For a homogeneous system, Ax is not this A, some matrix. So, matrix applied to x is equal to 0, null space of a matrix. If the matrix is invertible, what is the null space? No, for the matrix, what is the null space? Null space is a space. I am asking the space, not the dimension. If it is invertible, rank is full. So, what is nullity? 0. So, that means this null space should be 0 for that, right. If a matrix is invertible, its null space should be 0. So, let us look at the matrix of this one, a minus 2i, that is this matrix, right. And what is the determinant of this? It is 2 by 2. To find invertibility, I can just find out what is the determinant. What is the determinant? Is it 0? Is it 0 or not 0? 0? Okay. So, if it is 0, then what should happen? It should not be invertible, right. So, that means there is some solution, that is what we have gotten already, one vector is already there, right. So, this is a typo here. So, let us find out. So, what will be the dimension of this? How do I find the dimension of that null space? I have got a one vector. So, what shall I do? If I want to find the dimension of the null space, what shall I do? Let us look at, I want to find dimension of a minus 2i. So, what is a minus 2i? That is equal to minus, so that is minus 7, 2 and 2, right. Is that okay? That is a minus 2i. So, what is this equivalent to? How do we find the solution space? How do you find the solution space? Say, I will reduce it to row equivalent form, right. So, what you should, so anyway 2 columns are coming equivalent, right. So, what is going to be the rank? Already we know it is to be, at least it is 1, it is equal to 1. So, only one solution is possible for the null space, right. Is it okay? If I look at the column, you can look at the column also, we have shown that column rank is same as the row rank, right. So, for the null space, for this dimension has to be equal to 1, it cannot be 2, right, because we found the rank is equal to 1, right. So, nullity is equal to 1, dimension is 1, and we already have one non-zero vector, 1 minus 1, right. for which we have shown that, that is on the solution set. So, dimension is equal to 1. So, the question comes, does there exist some other scalar for this matrix, right? We have got the scalar 2, right, and we got a vector 1 minus 1. So, that A applied to 1 minus 1 is equal to 2 times 1 minus 1. Question is there some other scalar also and some other vector which has a similar property, right? So, how does one find out that scalar? So, what we want to do? We want to find out a scalar lambda such that A minus lambda I applied to x is equal to 0, and we should have a non-zero vector x. Earlier I just gave you as a sort of without any motivation why I should take 1 minus 1. I said 1 minus 1 has that property and scalar comes out 2. So, here if this is equal to 0 for a non-zero scalar x, that means what? That means this matrix A minus lambda I for that scalar cannot be invertible, because already a non-zero solution is there, right. It cannot be invertible, right, because if it is invertible, only solution possible is x is equal to 0, right. For a homogeneous system, the only solution possible is 0 if and only if the matrix is invertible, right. So, if a non-zero solution is obtained, some matrix applied to x is equal to 0, x is non-zero, that means this matrix cannot be invertible, it has to be singular. If it is singular, what should happen? Determinant of that should be equal to 0, right. So, if this is true, then A minus lambda I cannot be invertible, so its determinant must be equal to 0, right. So, that means what? So, let us find out that. So, let us look at A minus lambda I. Okay. Determinant of that, okay, equal to 0. What does that give you? Determinant of this is equal to 0. So, giving that minus 5 minus lambda, right, 4 minus lambda multiplied by minus plus 14. Okay. What is this 7? I think there is some mistake here, right, typo. What is the determinant of this? Let us just compute. I think while typing some mistakes have come. So, let us look at the matrix is 5 minus lambda minus 7, 2 and 4 minus lambda. So, that is A minus lambda I, A minus, right, this is the matrix. So, what is the determinant of this? So, that is 5 minus lambda, 4 minus lambda plus 14, right. So, what is that equal to? Let us compute 20 minus 4 lambda, 20 minus 4 lambda minus 5 lambda, that is, I think that this is minus 4 here in the matrix, yes, okay. Minus 5 minus 7. So, there is a minus here, that is plus 4 as it is, okay. So, that is minus 5 minus lambda, 4 minus lambda, and this is plus 14, that is okay, right. So, that gives me minus 20 minus 4 lambda plus 5 lambda plus lambda square plus 14, right. So, what is that equal to? Lambda square plus lambda minus 6, right. So, determinant of this equal to 0 implies lambda square minus plus lambda minus 6 is equal to 0. So, what is that? Lambda plus 3 lambda minus 2 equal to 0. Is it okay? Going back to school, factorization, 6 factors 3 into 2, you want plus here. So, okay. So, that means lambda is equal to minus 3 and 2. That is how this scalar 2 has come in the beginning, right. and what I did for this scalar we solved the system a minus 2i x is equal to 0. That is a homogeneous system, I can get a solution of that. That is how it gave me 1 and minus 1, right. So, let us do it the same thing for the other one. So, let us do it for, okay, I think it is better to do the calculation by, okay. There may be typo, let us just see. So, lambda is minus 3, so a plus 3i. So, minus 5 plus 3 minus 7 2 4 plus 3, is that okay? So, that gives me minus 5 minus 2 minus 7 2 4 plus 3 7, right. So, let me clarify what I mean, and supposing a x is equal to lambda x, suppose for some lambda there is an x, right. If I multiply it by alpha x, will that be equal to lambda alpha x for any alpha? If this implies this, right. So, for the same scalar lambda, this also is a solution. So, and there is a vector on the same line, is alpha times that vector which we have 1 minus 1 chosen, so on, that is all, right. So, you take any vector on that is okay, that is what I meant, that, right, clear, okay. So, let us come back. So, I am looking at the solution for lambda equal to minus 3, a minus 3i, okay. Lambda is minus 3, so a plus 3i equal to 0. We are trying to solve this system. So, this is what it comes out. So, how do you solve the system? By reducing the matrix to the Ax is equal to 0, reduce the matrix to row equivalent form. So, it has 2 rows identical. So, that means I can subtract and I will get 0 0, right. So, this is row equivalent form. So, what is the solution? Minus 2 x1 minus 7 x2 equal to 0, right. So, you can put x2 any value and get the value for x1, right, or x1 is determined in terms of x2, right. So, if you do that, so that is what you get, minus 7 and 2, right, the vector is minus 7 and 2, or any scalar multiple of that, or any scalar multiple, is that okay? How do you get this one? By solving minus 2 x1 minus 7 x2 is equal to 0, right. So, solve that. So, what I get is this, I got 2 vectors and 2 scalars with the same property for this matrix, that A applied to 1 minus 1 is 2 times, it scales it by 2, and this vector is scaled by minus 3, right. So, let us try to combine these two in one equation. How do I combine that in one equation? I want to write one equation where both these are captured. So, let us call this as C1, call that as C2 and form a new matrix, right. Then what will happen? Let us call C1 equal to this and C2 equal to this. Then what is A of A applied to this matrix? It will be AC1, right, plus AC2, but AC1 is, what is AC1? That is the first lambda times that vector, second is second scaling second thing, right. It is just, right, first vector, second vector, and scaling is 2 and minus 3. So, I can write it as a matrix multiplication, and that is same as this matrix is same as C1 C2, and that is a diagonal matrix. So, the two equations have been put together into this equation now. And now look at this C1 C2, this matrix with this first column and this as the second column. Let us call that matrix as something, let us call that matrix as P, 1 minus 1 second column. This is the invertible matrix. What is the, right, is it invertible? Determinant not equal to 0. So, this is invertible. So, that equation A P equal to P times this diagonal matrix. P is invertible, so this is invertible, I can take it on the other side by multiplying by inverse of that. Yes, I can multiply on both sides, on the left by the inverse of this matrix. This is called P. So, P inverse A P will be equal to this diagonal matrix. Yes, is it clear? So, I am saying P inverse A P is equal to diagonal matrix. So, what we have done? What we have done is for this given matrix that we had, right, I have found two scalars, namely 2 and minus 3. What were these two scalars? They were the solutions of determinant A minus lambda I equal to 0. For each one of them, I solved the system of homogeneous system and found out, right. Here I was able to get one vector 1 minus 1, other one minus 7 and 2, say that the matrix found by them is invertible, and as a result I got P inverse A P is equal to diagonal, right. So, this is a process I have done by which I am able to find the diagonal entries of for that given matrix A. I am able to find the matrix P, say that this property holds. Is okay?